The universe began as a seething fireball of pure chaos. From that primordial anarchy, everything we know somehow emerged. Today we unlock a profound mystery: how the universe builds intricate order from chaos at every single scale. You will discover the elegant dance between randomness and structure that defines our very existence. How did a formless expanse give rise to the cosmic web of galaxies? What hidden force guides atoms to assemble into living beings? By the end, you will see the entire cosmos in a completely new light. What does it mean that we are part of this magnificent transformation? There was no space, no time, and no matter in the first fleeting moments. Our universe was a single point of unimaginable energy, a searing fireball where the forces that govern reality were fused into one. In this primordial state, the concept of here and there did not exist. The notions of before and after were meaningless. This was the ultimate form of chaos, a realm of pure, undifferentiated potential. Yet within this featureless inferno, the first whispers of structure were already stirring. Quantum fluctuations, tiny random variations in energy, flickered in and out of existence. These were not events in time, but spontaneous ripples in the fabric of reality itself. They were the universe's first and most subtle seeds of difference. In a perfectly uniform cosmos, nothing would ever change, but these infinitesimal imperfections created a faint, random pattern in the energy field. Slight overdensities and underdensities began to emerge, variations so small they are almost impossible to describe. From this seething, chaotic beginning, the first critical transition was moments away, a transformation that would unlock the forces of nature and begin the long journey from formless fire to the cosmos we recognize today. Then, in a flash of incomprehensible energy, the universe underwent a transformation that set the stage for everything to come. It did not simply expand, it exploded outward in a growth spurt of staggering violence and speed. In a span of time so brief it makes a heartbeat seem eternal, the fabric of spacetime itself stretched faster than light. This was the era of cosmic inflation, and it was the cosmos's first great act of imposing order on the primeval chaos. Those infinitesimal quantum wrinkles, the random flickers from the fireball's dawn, were suddenly stretched to monumental proportions. Imagine a tiny, intricate pattern drawn on a deflated balloon. Now, picture that balloon inflating to the size of the entire Earth in an instant. The pattern is still there, but its features are now imprinted across a vast landscape. This is precisely what inflation did. It took those minute quantum seeds and magnified them into the foundational blueprints for the entire cosmic web of galaxies we see today. In a beautiful paradox, this violent expansion also created a profound smoothness. It stretched the universe so thin and so fast that it ironed out any major wrinkles, leaving a cosmos remarkably uniform in temperature from one end to the other. Yet, it was not a perfect smoothness. It was a smoothness with a specific, imprinted pattern, a subtle tapestry of density variations woven directly into the fabric of spacetime. This explosive event demonstrates a powerful truth about our universe. A brief, rule-driven phase can sculpt a homogeneous landscape from pure randomness. It created the quiet, orderly initial conditions required for the next, more patient force to begin its work, setting the stage for the slow, relentless storytelling of gravity. After that explosive beginning, a new and patient force was waiting in the wings. While the strong and electromagnetic forces busied themselves with binding atoms and governing light, gravity began its slow, relentless work on the grandest stage of all. Gravity is the universe's great architect, a force so weak that a tiny magnet can defy the entire Earth's pull. Yet it gains immense power over vast distances and time. Its influence is cumulative, growing stronger as more matter gathers together. This gentle tug was all that was needed to begin sculpting the cosmos. It started with the faintest of whispers, a subtle pull on the sparse clouds of hydrogen and helium that drifted through the cooling darkness. Those tiny density variations, the quantum seeds magnified by inflation, became gravity's blueprint. Where matter was just slightly denser, gravity's pull was a tiny bit stronger, drawing in ever more gas from the surrounding areas. Over millions of years, this simple, attractive force began to carve magnificent structure out of a near-uniform haze. Vast nebulous clouds slowly collapsed under their own weight, becoming so dense and hot in their cores that they ignited, flooding the universe with light for the very first time. These were the first stars, and their birth was the moment gravity truly set the cosmic clock in motion, transforming a dark, simple universe into one brimming with complexity and potential. For eons, the universe was a silent, shadowy realm. This was the cosmic dark age, a time when vast clouds of primordial gas drifted through an expanding emptiness, with not a single star to pierce the gloom. But gravity was not idle. It continued its patient work, pulling together the largest of these pristine clouds, composed only of hydrogen and helium, into ever denser knots. Deep within these collapsing structures, pressure and temperature began to climb to staggering heights until a critical threshold was crossed. In a spectacular flash, nuclear fusion ignited. The first stars were born, and the cosmic dawn broke across the universe. These first stars, known to astronomers as population 3 stars, were nothing like our own Sun. They were colossal behemoths, hundreds of times more massive, and they lived fast and furious lives. Their immense gravity created furnaces of unimaginable heat, burning through their nuclear fuel in only a few million years, a mere blink in cosmic time. Yet within their brief, brilliant lives, they performed a miracle of cosmic alchemy. For the first time since the Big Bang, new elements were being forged. The simple protons of hydrogen were fused into helium, and then, under extreme temperatures and pressures, those helium nuclei were smashed together to create the first traces of carbon and oxygen. This was the universe's first step toward true chemical complexity. Before these stars, the periodic table was a sparse list of just 2 elements. Now, the building blocks for everything else were being created deep within these stellar crucibles. But the story does not end with their creation. The violent deaths of these first stars were just as important as their births. After burning through their fuel in a geological instant, they could no longer support their own immense weight. Their cores collapsed, triggering cataclysmic supernova explosions that outshone entire galaxies. In their final, glorious moments, these stars did not simply vanish. They scattered their newly forged riches far and wide, blasting carbon, oxygen, and other heavy elements out into the surrounding gas clouds. This was the first great act of cosmic recycling. The pristine interstellar environment, once composed only of the 2 simplest elements, was now seeded with the ash of dead stars. This enriched cosmic stew, now containing the essential ingredients for rock, water, and air, was the prerequisite for everything that followed. The universe was no longer a simple place. It was now prepared for a new generation of stars, for the formation of planets, and for the eventual rise of life itself. With the seeds of creation sown by the first stars, the universe was ready for its next masterpiece. Gravity continued its patient sculpting, pulling these enriched clouds of gas and stardust into structures of breathtaking scale and beauty. These were the first galaxies, vast islands of stars born from the ashes of their brilliant predecessors. Our own Milky Way is one such cosmic metropolis, a swirling disk of hundreds of billions of stars, with graceful spiral arms, a dense central bulge, and a vast, invisible halo of dark matter that binds it all together. But the Milky Way is not alone. It is just one of perhaps 2 trillion galaxies, each a dynamic system of stars, gas, and dust, all dancing to the tune of gravity. And these galaxies did not emerge in isolation. They began to find each other, drawn together across the vast emptiness by their mutual gravitational attraction. They clustered into groups, and those groups gathered into immense clusters, which themselves formed long chains and great walls. This is the cosmic web, the largest structure in existence. Picture a sponge or a network of neurons in a colossal brain, with galaxies tracing out luminous filaments that stretch for hundreds of millions of light years. Between these brilliant strands lie the cosmic voids, immense and nearly empty deserts of space. This is not a random scattering. This grand architecture is a direct, frozen record of the universe's earliest moments. The pattern we see today, with its filaments and voids, is a gigantic echo of those minute quantum ripples from the fiery dawn, amplified by inflation and meticulously carved over billions of years by the relentless pull of gravity and dark matter. It shows us that the order we see on the largest scales, a tapestry woven across the entire observable universe, was encoded in the first instance of time. The universe took its initial chaos and, through simple, persistent rules, built a scaffold of staggering complexity. But this cosmic web was not the end of the story. It was merely the stage, a grand new arena where the laws of physics could begin an even more intricate kind of construction, one that would eventually lead to the chemistry of life itself. Yet within these colossal galactic cities, a more intimate and intricate form of construction was also underway. Around newborn stars, vast disks of leftover gas and dust began to swirl, a chaotic, turbulent environment reminiscent of the universe's own fiery beginnings. In these stellar nurseries, countless microscopic particles of rock and ice were ceaselessly colliding, a frantic, random dance. But amidst this chaos, a simple, elegant process took hold. When two particles met, they did not always shatter apart. Sometimes they stuck together, held by weak electrostatic forces, like cosmic dust bunnies. This was the humble start of accretion. These tiny clumps continued to grow, their collective mass slowly increasing. As they became larger, their gravitational pull strengthened, allowing them to draw in more material from their surroundings. Over time, these random gatherings of dust evolved into kilometer-sized bodies called planetesimals, the building blocks of planets. The chaotic cloud was beginning to organize itself. The system started to clear its own house, with these growing protoplanets sweeping their orbital paths like cosmic street cleaners. Their gravitational interactions began to sort the entire disk. Lighter gases like hydrogen and helium were pushed to the colder outer regions, where they could be captured by the largest protoplanets to form gas giants. Heavier elements and rocks remained closer to the star, coalescing into dense, terrestrial worlds. From a formless, swirling disk of debris, a structured solar system emerged, with distinct zones and planets following stable, predictable orbits. Our own solar system, with its inner rocky planets and outer gas giants, is a perfect example of this self-organizing miracle. It created stable, lasting environments around a steady star, setting the stage for the next, even more astonishing, chapter in the universe's story. The chaotic dust had settled into ordered worlds, and on at least one of those worlds, the conditions were now perfect for something truly extraordinary to begin. Our own world is a perfect example of this cosmic balancing act. Earth is a planet of incredible dynamism, a world constantly suspended between the forces of chaos and order. Beneath our feet, the mantle churns like a slow, geological pot of soup, driving the immense plates of the crust to collide and pull apart. This process builds mountains and opens ocean trenches, reshaping the very face of the planet over millions of years. Above us, the atmosphere is a turbulent river of gas, where the sun's uneven heating creates vast weather systems, from gentle breezes to howling hurricanes. This is not a world at rest. It is a system far from equilibrium, a place of constant flux and energy flow. Yet, from this relentless dynamism, something remarkable emerges, a global stability that has persisted for eons. Complex, self-regulating cycles have arisen. The carbon cycle, for instance, acts as a planetary thermostat. Volcanoes belch carbon dioxide into the air, while weathering rocks and growing organisms pull it back out, maintaining a balance that has kept our climate within a habitable range for billions of years. Our planet's molten core generates a powerful magnetic field, an invisible shield that deflects the sun's harmful radiation, protecting the fragile chemistry at the surface. This reveals a profound truth about how order is built and maintained in our universe. Stability is not the absence of change. It is a dynamic process, a dance. It is a state that is actively maintained through continuous flows of energy, from the sun's rays to the planet's internal heat, and through intricate feedback loops that keep the entire system in check. This principle of dynamic equilibrium applies from the geology of a single world to the potential for life on any other. A truly dead world, one that is static and perfectly balanced, could never host the persistent, evolving complexity we see here. It is the very turmoil, the constant push and pull, that creates the conditions for lasting order to flourish. The early Earth's oceans were a roiling, chaotic broth. They simmered with volcanic heat, lashed by ultraviolet rays from a young sun, and churned by constant impacts. In this turbulent prebiotic soup, simple molecules like water, ammonia, and methane collided at random, a frantic chemical dance with no director. Yet within this apparent disorder, something miraculous was brewing. The constant energy input from sunlight and geothermal vents acted like a cosmic stirrer, pushing these simple ingredients to form more complex carbon-based compounds. Amino acids, the building blocks of proteins, and nucleotides, the subunits of genetic code, began to accumulate. For a long time, this was just a rich organic mixture, a non-living chemistry set. But then, a threshold was crossed. Among the countless random interactions, a molecule, perhaps a form of ribonucleic acid, or RNA, stumbled upon a remarkable trick. It learned to copy itself. It was not a conscious act, but a simple mechanical process driven by chemical attraction. A strand of this molecule could act as a template, attracting and binding complementary pieces from the surrounding soup, assembling a mirror image of itself. This was the moment the universe crossed a new frontier. It was the transition from non-living chemistry to biological information. The emergence of that first self-replicating molecule represents one of the most profound leaps in cosmic history. It suggests that under the right conditions, with a constant flow of energy and a diverse mix of ingredients, the laws of physics and chemistry inherently favor the rise of complexity. Random collisions, given enough time and the right environment, can give birth to a system that captures order and perpetuates it. This was not a carefully planned event. It was chaos discovering a recipe for its own continuation. From that point on, a new kind of cosmic order was unleashed, one based not just on gravity or thermodynamics, but on information. A molecule that could copy itself even imperfectly had opened the door to evolution, setting the stage for a living universe capable of learning, adapting, and eventually looking back upon its own origins. That first self-replicating molecule unlocked a new kind of cosmic power, the principle of biological self-organization. Watch a single fertilized egg cell, a microscopic sphere containing a full set of genetic instructions. It divides not into a disorganized blob, but into a symphony of coordinated activity. One cell becomes 2, then 4, then 8, each division guided by an internal script. Chemical signals flicker between these cells, telling them where to go and what to become. Some are instructed to form nerve tissue, their long fibers reaching out to create a network for thought and sensation. Others are directed to become muscle cells, capable of contraction and movement. Still others become the intricate filtering units of a kidney or the light-sensitive rods and cones of an eye. From that one simple starting point, a staggering diversity of cell types emerges, all communicating and cooperating to build a single, unified organism. This is not a random assembly. It is a deeply patterned process, where local interactions following simple rules give rise to global, intricate order. The genetic blueprint provides the basic rules, but the emergent structure, the living, breathing body, is far more than the sum of its parts. This same principle of self-organization scales up to encompass the entire living world. A tropical rainforest or a coral reef is a vast, pulsating network of countless species. Predators and prey, pollinators and plants, decomposers and producers, all locked in a delicate dance of competition and cooperation. A wolf hunting a deer seems like pure conflict, but that interaction regulates populations, which in turn affects the vegetation, which influences the soil, creating a cascade of effects that stabilizes the entire ecosystem. This intricate web results in a community that is remarkably resilient, able to withstand and recover from shocks. How do these living systems accomplish this feat? They are constantly fighting a fundamental cosmic trend toward disorder. A cell, a body, or a forest is a localized pocket of intense organization, and it maintains this order by consuming energy and exporting entropy, which is the measure of chaos, back out into its surroundings. A tree takes in disordered sunlight and simple molecules, uses them to build its complex, ordered structure, and releases waste heat and gases, which are a more disordered form of energy. It is literally feeding on chaos to build and sustain its own internal order. This process builds layers of complexity, from the molecular machinery inside a cell to the global nutrient cycles of the biosphere, all governed by the relentless editing of evolution. Life is the universe's most sophisticated method for transforming random energy flows into enduring, dynamic structures. The human brain is a universe in miniature, a 3-pound web of nearly 100 billion neurons. Each neuron fires in a storm of electrochemical signals, a seeming chaos of individual sparks. Yet from this bustling internal network, something unified and profound emerges: your stream of consciousness, your sense of self, your memories and dreams. This is the universe building order at the most intimate scale, transforming random neural noise into the structured symphony of a mind. And these minds, in turn, connect. Our seemingly random individual experiences and ideas collide and interact. From this social chaos, human societies self-organize into something greater. No single person sat down and invented language, yet this intricate system of grammar and meaning emerged from countless interactions. No central planner designed the first economy, yet patterns of trade and value arose spontaneously from people's individual needs and choices. Laws, technologies, and scientific knowledge all follow this same pattern. They are not handed down from on high. They are emergent phenomena, vast structures of order crystallizing from the bottom up. This represents a new and astonishing tier of cosmic organization, where information itself becomes the primary structuring principle. We are not just building with matter and energy anymore, we are building with ideas. Our unique ability to create abstract models of the universe, to imagine things that are not right in front of us, and to share that knowledge across generations has unlocked a new kind of evolution. Cultural evolution operates at a pace that dwarfs biological change. A new idea can circle the globe in hours. A new technology can reshape civilization in a century. This is not merely a metaphor. It is a physical process, a new layer of the universe's endless quest for structure. Through our collective minds, the cosmos has found a way to become aware of itself. We are the universe, looking back at its own history, contemplating its own laws, and now, actively and consciously participating in the grand and ongoing creation of order from chaos. A sprawling city at rush hour is a spectacle of apparent chaos. Millions of people move in every direction, vehicles clog the streets, and countless individual decisions are made every second. Yet, if you rise above it all, a hidden order reveals itself. Traffic, for all its frustrations, flows in predictable patterns, governed by traffic lights and shared rules of the road. Economic markets, vast networks of buyers and sellers, self-organize to set prices and distribute goods with an efficiency no central planner could ever design. Even our social lives form intricate, invisible webs of connection. These are not accidents. A city is a complex adaptive system, a living entity built from the bottom up. Its order is not imposed from the top down by a single architect, but emerges spontaneously from the interactions of its countless inhabitants, each following their own simple, local rules. You decide your route to work based on traffic. A shopkeeper sets a price based on supply and demand, and a group of friends plans a meeting at a local cafe. None of these individual actions is planning the city itself, yet collectively, they generate a resilient, dynamic, and constantly evolving whole. This emergent order makes cities incredibly robust. A single road closure causes traffic to reroute itself organically. The failure of one business creates an opportunity for another. This resilience, born from countless local adjustments, mirrors the way gravity pulls stars into galaxies. On a vastly different scale, both are stories of simple rules giving rise to magnificent, unplanned structure. But cities do more than just resist collapse. They actively foster innovation. The dense concentration of people and ideas creates a crucible for creativity, where random encounters and the collision of different perspectives can spark new inventions, new art, and new ways of thinking. This is the universe building order at a social and technological scale, proving that the same fundamental principles that built galaxies and stars are still at work, now weaving the fabric of human civilization itself. We have extended this cosmic dance into the realm of pure information. Our planet is now enveloped in a digital universe, a sprawling network of silicon and light built from human ingenuity. The Internet began as a chaotic web of disconnected pages, a digital primordial soup. Yet, from that initial anarchy, it self-organized. Search algorithms emerged as a new kind of gravity, pulling scattered data into constellations of meaning. Social platforms became digital galaxies, attracting billions of users who form communities and shape culture. This vast, interconnected structure did not arise from a single grand design. It grew from the bottom up, through countless individual contributions and interactions, mirroring the emergent order of a city or an ecosystem. Now, we are taking the next profound step, creating artificial intelligence. These systems are designed to do one thing exceptionally well: find subtle patterns in oceans of chaos. An AI can sift through trillions of data points, from medical images to financial transactions, and discern an underlying order that is completely invisible to us. It can predict a storm's path by analyzing a planet's worth of atmospheric data, or identify a promising new drug candidate by modeling the chaotic dance of millions of molecules. This is not just a tool for convenience. It is the universe's drive for structure and pattern finding, now manifesting through our own technological creations. We are building a new kind of mind, a non-biological intelligence capable of perceiving and constructing orders of complexity we can scarcely imagine. This intelligence may one day help us solve grand challenges, from climate modeling to unraveling the deepest mysteries of physics, becoming an active partner in the cosmos's endless quest to build ever more intricate and enduring forms of structure from the raw material of chaos. But to find the source of this cosmic creativity, we must journey to the very bottom of reality. At the tiniest of scales in the quantum realm, a strange and fundamental truth prevails. Perfect stillness and perfect order are not just absent, they are forbidden. This is the domain of Heisenberg's uncertainty principle, a law of nature that states we can never precisely know both the position and the momentum of a particle at the same time. The more you pin down one, the more the other becomes a blur of possibility. This is not a limitation of our measuring tools, it is a feature of the universe itself. The quantum world is fundamentally fuzzy, a seething, restless sea of energy. Even in what we call a perfect vacuum, empty space is not empty at all. It is a hive of frantic activity, a foam where virtual particles spontaneously pop into existence and then vanish almost instantly. They borrow energy from the void for a fleeting moment, a pair of particles and their antiparticles appearing together before annihilating each other, returning the energy loan. This constant, random flickering is the most basic form of chaos, woven into the fabric of space-time. Yet, paradoxically, this underlying turmoil is directly responsible for creating stable, measurable forces. Take the Casimir effect. If you place two perfectly smooth, uncharged metal plates incredibly close together in a vacuum, they are gently pushed toward each other. Why? Because the space between the plates is so narrow that only certain wavelengths of virtual particles can flicker into existence there. But outside the plates, all wavelengths can appear. The greater pressure from the particles outside forces the plates together. Here, the chaotic dance of virtual particles produces a predictable, orderly force. And this principle scales up to the grandest stage of all. Those primordial quantum fluctuations from the universe's first instant, the very same ones that were stretched into the cosmic blueprint by inflation, were born from this same quantum uncertainty. The entire majestic architecture of the cosmic web, with its galaxies and voids, can trace its lineage back to this seething, indeterminate foam. The bedrock of reality is not a placid, static foundation. It is a dynamic and creative tension, a perpetual dance between the chaos of indeterminacy and the emergence of stable particles and forces. The very building blocks of order are forged in the fires of fundamental randomness. This relentless drive for structure finds its ultimate validation in a seeming paradox within the laws of physics themselves. The second law of thermodynamics is famous for its grim prognosis, that the universe is on an inevitable slide toward maximum disorder, a state known as thermal equilibrium. Yet look around you. Life, civilization, and galaxies are all spectacular examples of increasing order. How can this be? The answer lies in a special class of systems that thrive far from that dull state of equilibrium. These are called dissipative structures. A whirlpool in a flowing stream is a perfect example. The whirlpool itself is a beautiful, coherent structure, a temporary pocket of spinning order. But it can only exist because the water is moving. It takes the energy from the stream's flow, uses it to maintain its spiral shape, and then dissipates that energy as friction and heat into the surrounding water. The moment the stream stops flowing, the whirlpool vanishes. It is a pattern sustained by its ability to constantly export disorder to its environment. This is precisely what a living cell does on a microscopic scale. It is not a closed, static box. It is a bustling factory that takes in concentrated energy from food or sunlight, uses that energy to build and repair its intricate internal machinery, and then expels waste products and heat, which are a much more disordered form of energy. The cell maintains its high internal order by increasing the disorder of its surroundings. This principle, articulated by the chemist Ilya Prigogine, shows that the second law is not violated but fulfilled in a more profound way. The overall entropy of the universe still increases, but that very increase can drive the spontaneous formation of local, complex order. These structures are not accidents. They are a natural and expected consequence of an open system with a constant flow of energy moving through it. From the swirling atmosphere of a hurricane to the global circuits of the ocean currents, we see the same process at work. Chaos is not the enemy of order, but its raw material. The universal trend toward dispersion provides the very engine that allows for the temporary, beautiful, and complex rebellion we call life. This same pattern whispers through the veins of a leaf and thunders across the cosmic web. Fractals are nature's recursive blueprint, a geometric signature written into everything from a flake of snow to the distribution of galaxies. A fractal is a shape of infinite complexity, built from the simple act of repeating a pattern at ever smaller scales. Pluck a single frond from a fern, and you will see it is composed of smaller fronds, each of which mirrors the shape of the whole. Look closer, and those smaller fronds are themselves made of even tinier, identical copies. This self-similarity, this nesting of patterns within patterns, is a stunningly efficient way to build complexity. It is a mathematical language that describes how a very simple set of rules, applied again and again, can spontaneously generate breathtaking order from an initial state of randomness. Consider a lightning bolt. Its path is a chaotic, jagged tear across the sky, a frantic search for the fastest route to the ground, yet its final form is not a random scribble. It is a fractal. The main trunk branches into smaller bolts, which then branch again into even finer tendrils, each fork a miniature version of the larger split. This structure emerges from a simple rule, following the path of least resistance through a turbulent atmosphere. The result is a pattern that is both unpredictable in its precise details and deeply ordered in its overall form. This is not just a curious feature of a few natural oddities. Fractals are everywhere. The branching of a tree's limbs optimizes its exposure to sunlight, while the branching of our lungs and circulatory systems maximizes surface area within a limited volume. A river delta carves the same branching pattern into the landscape as it seeks the sea. Even a head of broccoli reveals a miniature forest of self-similar stalks. This prevalence points to a profound truth about our universe's operating system. The cosmos has a preferred method for building complex, robust structures, and it relies on recursion. It takes a simple algorithm and runs it endlessly, allowing for infinite variation within a consistent theme. This recursive process is a powerful engine for creating order, because it can build staggering complexity from a very small amount of information, just a few simple rules repeated into infinity. The universe does not need a separate blueprint for every leaf on a tree or every tributary in a river network. It just needs one good fractal rule, and then it lets the chaos of the environment shape its unique yet familiar expression. Even the most predictable systems can harbor a deep-seated turbulence. Take a simple pendulum, its rhythmic swing a classic symbol of order. Now, imagine giving it a double joint, creating a double pendulum. Release it from your hand, and for the first few swings, its motion seems logical. But then, something extraordinary happens. Its movement becomes wildly erratic, a frantic, flailing dance that is completely impossible to predict. This is the essence of chaos theory, a revelation that within the heart of deterministic systems, those governed by fixed laws, can lie an inherent and profound unpredictability. The system is not random. If you knew the exact starting position and velocity down to an infinite decimal, you could, in theory, plot its entire path. But in our real world, that is an impossible task. The tiniest, most imperceptible variation in how you release it, a difference smaller than the width of an atom, will lead to a completely different flailing pattern just a minute later. This is the famous butterfly effect, the poetic idea that the delicate flap of a butterfly's wings in Brazil could set off a chain of events in the atmosphere that ultimately alters the path of a tornado in Texas. It is not that the butterfly causes the storm, but that its tiny influence is amplified exponentially through a complex, interconnected system, steering the outcome down one path instead of another. This sensitive dependence on initial conditions means that the long-term future of chaotic systems is fundamentally unknowable to us. We can never measure the starting state of the atmosphere or a double pendulum with perfect precision. Yet, within this apparent madness, a hidden order emerges. If you map the chaotic motion of that double pendulum not in physical space, but in an abstract mathematical realm called phase space, a beautiful and intricate shape appears. This is a strange attractor. No matter how erratic the pendulum's movement seems, its path in this phase space will always be drawn toward this complex, fractal-like structure. It will never repeat itself, yet it will never stray from this underlying form. The chaos is not random. It is a form of order so complex and intricate that it appears random to our limited perception. The whirl of a galaxy, the turbulent flow of a river, the fibrillation of a human heart, all can be governed by these strange attractors. The universe is showing us that its deepest order is not always simple and repetitive. Sometimes, the most stable and enduring order is a chaotic dance, forever exploring the boundless possibilities contained within a beautiful, invisible shape. The universe began in a state of perfect but sterile symmetry. All the forces we know today, gravity and electromagnetism, the strong and weak nuclear forces, were fused into a single, undifferentiated superforce. In that primordial heat, every particle was identical, massless, and moved at the speed of light. It was a universe of supreme unity, but also of profound simplicity, where the concept of difference could not exist. Then, as the young cosmos expanded and cooled, it crossed invisible thresholds. Phase transitions rippled through the fabric of reality, moments akin to steam condensing into water, or water freezing into ice. With each transition, a fundamental symmetry was spontaneously broken. The first great separation saw gravity peel away, carving out the arena of space-time itself. Then, in a pivotal moment, the electroweak force fractured into the electromagnetic force, which gives us light, and the weak nuclear force, which governs radioactive decay. This was not a violent rupture, but a cosmic unveiling. As the Higgs field, which had been dormant, suddenly activated, it was like an invisible molasses flooding the universe. Particles that once raced around at light speed began to drag, slowed by their newfound interactions with this field. They acquired mass, and in that single transformational event, the universe gained texture. Electrons, quarks, and neutrinos were no longer identical. They took on their distinct identities, their different weights and properties. This breaking of symmetry was the genesis of diversity. A perfect, featureless unity gave way to a reality rich with variation and potential. The very laws of physics themselves became more specific, more nuanced. This is the hidden engine behind the cosmos's creative power. Order does not always emerge from meticulous planning. Often, it blossoms from a necessary and beautiful breaking of the mold. The homogeneous perfection of the beginning was a blank canvas. It was only when that symmetrical state fragmented that the ingredients for stars, planets, and life itself could step onto the stage. This perspective leads us to a radical idea, one that reshapes our understanding of reality itself. Information may be far more than a human abstraction. It could be a fundamental property woven into the fabric of the cosmos, as real and tangible as matter and energy. Think of the laws of physics not just as rigid rules, but as cosmic algorithms, a set of instructions that the universe is constantly running. When gravity pulls a cloud of gas into a star, it is not merely moving matter, it is processing information. The random positions and velocities of countless atoms are taken as input, and through the relentless application of physical law, they are transformed into a new, highly ordered output, a luminous sphere with a complex internal structure. The star has, in a very real sense, computed its own existence. This computational view extends to the very story of life. Evolution is a grand billion-year, long information processing system. Genetic code is data, stored in the molecule of DNA. Random mutations are like random bits being flipped in that code, and natural selection is the algorithm that tests these new programs in the harsh environment of reality, discarding the faulty code and preserving the successful information. Life is a process that accumulates, refines, and transmits information across generations, building ever more sophisticated forms of order. This is the essence of the bit-from-bit proposal, championed by the physicist John Archibald Wheeler. He suggested that every particle, every field of force, every facet of reality, ultimately derives its existence from binary answers to yes or no questions, from bits of information. In this view, the cosmos is not simply described by mathematics. It is a vast, ongoing computation. The emergence of order at every scale, from the quantum foam to the galactic web, is the output of this cosmic computation, the result of the universe processing its own inherent information. We are not just living in a universe that contains information. We are living inside a universe that is information, a dynamic, self-organizing system whose very substance is the act of turning chaotic data into structured, enduring meaning. So this grand cosmic story reveals a stunning trajectory when viewed from the beginning. The journey starts with a formless sea of energy condensing into the first subatomic particles, quarks and electrons. These particles then organized into stable atoms, primarily hydrogen and helium. Those atoms in the cold depths of space, later linked together to form the first simple molecules. On at least one world, those molecules assembled into self-replicating cells, which over billions of years diversified into the incredible tapestry of life, culminating in beings capable of looking up and wondering how they got here. This is not a straight and steady march upward. It is a story of fits and starts, of dead ends and catastrophic resets, with progress often emerging from the ashes of destruction. A supernova must shatter a star to forge the heavy elements essential for planets and life. Yet, through it all, a profound trend is undeniable, a clear arc from the utterly simple to the breathtakingly complex. How can this be, when the universe is supposedly doomed to a fate of maximum disorder? The answer lies in a beautiful cosmic bargain. Each leap in complexity, the formation of a star, the birth of a cell, the ignition of a conscious thought, is a local act of rebellion against entropy. These pockets of intense order can only form by exporting their chaos outward. A living organism maintains its intricate internal structure by consuming energy and releasing waste heat, a far more disordered form of energy, into its environment. The local order increases, but the total disorder of the universe increases even more, perfectly satisfying the second law. This grand narrative implies something truly wondrous about the nature of reality. The universe's fundamental laws and constants seem perfectly tuned, almost as if pre-loaded with a latent potential for complexification. The strength of gravity, the charge of an electron, the nuclear forces that bind atoms, all appear set to values that allow this multi-billion-year story to unfold. It suggests that given enough time and the right conditions, the emergence of ever more intricate and novel forms of order is not an accident, but an inherent potential written into the cosmic code from the very first moment. This elegant cosmic dance, building from particles to minds, forces a profound question upon us. Why is our universe so perfectly set up for this journey? The fundamental numbers that govern reality, the strength of gravity, the mass of an electron, the precise power of the nuclear forces, all seem suspiciously fine-tuned. If gravity were just a tiny bit stronger, the universe would have collapsed back on itself in a catastrophic crunch long before stars could form. If it were slightly weaker, matter would have flown apart too quickly to ever clump together into galaxies. The same delicate balance applies to every other constant. It is as if the cosmic dials were set with exquisite care to precisely the values needed for a universe that could eventually come alive. This remarkable observation is what scientists call the Anthropic Principle. In its simplest form, it states that the universe we observe must be compatible with the existence of observers with us. At first, this can sound almost trivial, but its implications are staggering. One compelling explanation for this apparent fine-tuning is the concept of a multiverse. Imagine our entire cosmos, with its specific set of physical laws and constants, is not the only one. It is merely one bubble in a vast, frothing meta-cauldron of universes, each with its own random set of rules. In most of these other universes, the numbers are all wrong. Gravity is too strong, or electromagnetism is too weak. These cosmic failed experiments may flash into existence and then vanish, or they may persist as barren, empty, or chaotic voids where atoms never form and stars never shine. We, of course, find ourselves in one of the exceedingly rare universes where the numbers just happen to line up. We are the lottery winners in a cosmic game of chance, living in a reality where the constants allow for the long chain of events that leads from the Big Bang to beings who can ponder it all. This does not diminish our universe's majesty, it reframes it entirely. Our beautifully ordered cosmos is not an inevitable product of a single set of laws. It is a special garden that has managed to grow in a vast desert of impossibility. The potential for order exists wherever the laws of physics permit it, and in our case, they permitted a spectacularly long and creative run. We are not the preordained goal of the cosmos, but we are a breathtaking testament to what is possible when chaos stumbles upon the right recipe. So much of the cosmic order we have mapped is built from things we cannot see. For every galaxy, star, and planet that glows in the night sky, there exists 5 times more matter that is completely invisible, a mysterious substance we call dark matter. We cannot see it, touch it, or trap it in a laboratory, yet we know it is there because of its immense gravitational pull. This invisible scaffolding is what holds the universe together. Without dark matter's gravitational anchor, galaxies would simply fly apart as they spin. The visible stars alone do not provide enough gravity to keep themselves bound. Dark matter forms vast, diffuse halos around each galaxy, a hidden skeletal structure upon which the luminous matter of stars and gas can gather and condense. It was the gravitational pull of these dark matter halos that first drew in the primordial hydrogen, creating the dense pockets where the very first stars could ignite. On the largest scales, it is the distribution of dark matter that traces out the magnificent filaments of the cosmic web, with galaxies merely being the glittering lights strung along its invisible lines. Yet for all its foundational power, dark matter is only half the story of the unseen cosmos. A second, even more mysterious force is at work, shaping the universe's ultimate destiny. We call it dark energy. While dark matter pulls the cosmos together through gravity, dark energy does the very opposite. It is a repulsive force woven into the fabric of space itself, causing the expansion of the universe to accelerate. Think of the universe as a loaf of raisin bread rising in the oven. For billions of years, the raisins, which are the galaxies, were moving apart as the dough expanded. Dark energy is like a sudden, powerful yeast that makes the dough rise faster and faster, pushing the raisins apart at an ever-increasing rate. This discovery overturned our most fundamental assumptions about the cosmos's future. We once imagined a universe that might eventually slow down and collapse back on itself. Now we see a cosmos destined for perpetual, accelerating expansion, growing colder and more isolated as galaxies are pushed beyond each other's horizons. Together, these two unseen components rule the cosmos. Dark matter, the great architect, builds the structures. Dark energy, the great repulsor, dictates the final scale of the cosmic stage. Their existence is a humbling reminder that the beautiful order we perceive, from the spin of a single galaxy to the vastness of the cosmic web, is governed largely by forces that remain hidden from our direct perception. The universe has shown us its magnificent structure, but it is also telling us in no uncertain terms that we are only just beginning to read the blueprint. 1,000 fireflies can blink in the darkness, each a tiny, independent lantern. Yet on a summer night, something magical happens. Without any signal, without a leader, they begin to flash in perfect, silent unison, their random flickers merging into a single, pulsing wave of light. This breathtaking display is not magic. It is synchronization, a powerful and universal mechanism for creating spontaneous order. Each firefly is a simple oscillator with its own internal rhythm. But when they can see each other's flashes, a subtle feedback loop is created. A nearby flash encourages a firefly to adjust its own timing just a little to match its neighbor. This tiny local interaction, repeated thousands of times across the swarm, cascades into a global consensus. The chaotic blinking of individuals gives way to the hypnotic, coordinated pulse of the collective. This same principle operates deep within your own mind. Your brain is a swarm of nearly 100 billion neurons, each one an independent cell that can fire an electrical signal. When you form a single thought or memory, it is not the action of one lone neuron. It is the synchronized firing of a vast, intricate network, a momentary consensus that emerges from countless local conversations. A thought is, in essence, a flash of lightning in a neural swarm, a fleeting but powerful order born from chaotic, individual activity. This phenomenon is everywhere once you know to look for it. The coordinated chirping of crickets, the mesmerizing schooling of fish that moves as one giant organism, even the rhythmic clapping of an audience that suddenly falls into perfect time, all are examples of this emergent lockstep. It appears in the invisible world of chemistry, where the concentration of molecules in a solution can begin to oscillate in unison, and in the realm of advanced materials, where electron pairs in a superconductor synchronize their waves to allow electricity to flow with zero resistance. The profound lesson here is that a conductor is not required for an orchestra to find its rhythm. Complex, coordinated behavior can arise from the bottom up, through nothing more than simple components following simple rules and communicating with their immediate neighbors. The universe has yet another elegant and powerful recipe for transforming isolated chaos into a unified, harmonious whole, proving once more that order is not always imposed from the top down, but often whispers its way into existence from the ground up. A towering redwood tree does not survive 1,000 years by remaining perfectly still. It sways with the wind, its flexibility preventing a catastrophic snap. This is the secret of resilience, a quality woven into the most enduring forms of order across the cosmos. True stability is not a static, brittle state. It is a dynamic and fluid capacity to adapt. Consider a forest after a devastating wildfire. The scene appears to be one of pure destruction, a landscape reduced to ash and charcoal. Yet, this very chaos triggers a profound renewal. The fire's heat opens the cones of certain trees, releasing seeds. The cleared canopy allows sunlight to reach the forest floor, spurring the growth of new, diverse seedlings. The ash itself enriches the soil. The ecosystem does not simply return to its old state. It reorganizes, often emerging with greater biodiversity and robustness than before. The fire was not an end, but a brutal, necessary part of the forest's long-term cycle. It pruned the old to make way for the new, demonstrating that the system's core function, to be a living, growing forest, was not destroyed but revitalized by the disruption. This principle scales to the most complex human systems. An economy is not a rigid machine. It is a living, breathing network of countless transactions, innovations, and decisions. A recession is a painful economic fire, a period of contraction and failure. Yet, within that turmoil, Inefficient businesses that resisted change may collapse, while more agile and innovative companies adapt and rise. The system, as a whole, purges its weaknesses and reorganizes around new strengths, often leading to new industries and a more resilient economic structure. This dynamic stability is a higher, more sophisticated form of order. It does not fight against randomness and change. It incorporates them. It uses disruption as a catalyst, a source of information that forces adaptation and learning. The most fragile order is a perfectly balanced house of cards, destroyed by the slightest breeze. The most robust order is a mature forest, a thriving city, or a healthy mind, each one a system that has learned to dance with chaos, using its energy not for collapse, but for its own continual evolution and renewal. The long-term forecast for our universe is a gradual, chilling fade to black. Billions of years from now, the last stars will flicker out, their fuel exhausted. Galaxies will drift apart into an ever-expanding emptiness, their lights vanishing over the cosmic horizon. The universe will approach a state known as the heat death, a final equilibrium where energy is spread perfectly thin and evenly across an unimaginable void. In this state, no temperature differences exist, no work can be done, and no new structures can form. It is the ultimate victory of entropy, a silent, static sea of maximum disorder where the cosmic story seems to end. Yet, even in this seemingly final chapter, the plot may still hold a twist. Some cosmological theories propose a far more dramatic finale. What if our universe is not a one-time event, but merely one cycle in an infinite series? In a cyclic universe model, the relentless expansion driven by dark energy may eventually reverse. After trillions of years, the cosmic repulsion could weaken, allowing gravity to finally take command. All of existence would begin to contract, falling back in on itself in a great cosmic crunch. This collapse would not be an end, but a reset. The universe would be compressed back into an ultra-hot, ultra-dense state, perhaps triggering a new Big Bang and birthing a fresh cosmos from the ashes of the old. In this view, the universe breathes, expanding and contracting in an eternal return, with each cycle creating its own unique tapestry of order from the primordial chaos. Another possibility is the quantum bounce, where the universe avoids a true singularity and instead rebounds directly into a new expansion phase. These ideas force a profound shift in perspective. The magnificent order we see around us, from the spiral of a galaxy to the consciousness reading these words, may not be a permanent feature of reality. It could be a temporary, brilliant phase, a magnificent bloom that appears only during the cosmic spring of each cycle. We are living in a golden age of structure, a fleeting epoch where the constants and conditions are just right for complexity to flourish before the long winter of equilibrium sets in. This makes our existence and our ability to comprehend this grand narrative infinitely more precious. We are not just passive inhabitants of a static cosmos. We are a momentary spark of awareness, a part of the universe that has temporarily organized itself to look back and marvel at its own origins and its ultimate fate. Our quest for understanding is the cosmos becoming conscious of itself, a beautiful and transient rebellion against the silent, cold statistics of the void. Our journey from the quantum foam to the conscious mind has traced a single, magnificent arc. We have witnessed a universe that is not passively sliding into a final disorder, but one that is perpetually, vibrantly engaged in a creative dance. At every scale, from the gravitational collapse of a galaxy to the synaptic flash of a thought, we find the same elegant principles at work. Self-organization builds complexity from the bottom up. Flows of energy sustain temporary islands of intense order. Information is processed, refined, and transmitted, turning raw data into enduring structure. This is the cosmos's great and ongoing project, building intricate, temporary castles from the ceaseless tides of chaos. This profound understanding transforms our own role in the story. We are not mere bystanders watching a cosmic spectacle unfold. We are active participants, living expressions of this universal drive toward structure. Every time we learn a new skill, build a connection with another person, or create something new, we are contributing to this grand, multi-billion-year process. The next time you look at a branching tree, the swirling cream in your coffee, or the bustling life of your own city, you can see it. You can witness the beautiful, dynamic struggle between randomness and pattern unfolding right before your eyes. We would love to hear what part of this grand narrative resonates most deeply with you. Share your thoughts and reflections in the comments below. And if you are eager to continue exploring the profound mysteries of the cosmos, be sure to subscribe and join us on the next journey.